Hello. Um, Today I'm gonna talk about something which is a little bit different from really using the software, even though I'm gonna show you how to use the software to figure out a common question, which is I have data, um, and these are the data we're gonna talk about, and I would like to fit these data. And how many different features, either populations in modeling or unified fit levels, should I use on this? That is a critical information because it will uh, eventually give you the complexity of the model you can fit. And obviously, more complex model with more population you have, better fit you're gonna get, but does it still make sense? At some point, you're gonna fit to a curve which is relatively featureless, but you're gonna fit to it a model which may have 20, 30 parameters, and you can fit an elephant to it. That's not a problem with that number of parameters. So the question really is, how many parameters does the curve support? How many do I need? How many should I use for this specific model? Now, to be fair, this question is really should not be solved in a software. You should not be using software to figure it out. You should actually start with understanding the microstructure. And in this specific case, the users have provided pictures. Um, and you can see that this is a kind of bicontinual system. You get basically something which looks like a foam or complex structure, which is composed of something which are probably voids and things which are, solid. And the question is, what can we resolve? What can we get from this? So I'm going to put this aside. So the curve which we measured is this. This is a relatively large range of sizes obtained on my SAXS instrument. If you look on the start of the data, which is out here, it's 10 to minus 4 inverse angstroms. 10 to minus 4 inverse angstroms is, I don't know, 5 or 6 microns, depending on how you calculate that. So you're looking on micron sizes, and to the other side, if you go all the way here, this is about 1 angstrom. So this is like in angstroms, in sizes. And somewhere in between, you get practically all the SAXS and most of the USAXS data Q range. And so principally you can see everything from a single nanometer features all the way up to micron features. That is kind of unusual. You really need for that a USAXS, SAXS, and instruments to combine together. But if you're lucky and have that, you can now characterize microstructure of the very wide range of sizes. But again, how many features can I distinguish here? And in order to do this, I'm going to try to do a little quick, very, very approximate explanation of what can be done or what the options are. This is the most crudest approximation of analysis of small angle scattering data you can imagine. And if you want to read it, there's a description here, so about what we have. So for the purpose of this model, I'm just made an assumption that I have something like polycarbonate with density of 1.2 or so grams per cubic centimeter, and around that is water. It's probably not true. I'm sure it's not true about these samples, but what that does, it gives me a delta rho square, which is really the contrast of those features. And then I went in and said, okay, well, first thing is let's talk about what the options are and what the model is. So I generated here, this is using the modeling package, and I generated for population 1, I generated a model structure. So I use this model here, and I generated over a range of sizes, which is unreasonably large. 10 to minus 5 inverse angstroms is achievable on probably just one USANS instrument in the world. Even my high resolution USACS would start at 3 times 10 to minus 5. So If you look on this, 1 times 10 to minus 5 inverse angstroms gives you about a diameter of about 60 microns. So that is really, really large. But I wanted to show you something there. The other thing is I went to the maximum value of 1. Again, that's where, you know, you basically need the wax detectors in the SAXS devices, which we often have. And I generated 400 points in between. So these are now data. Now, what are the choices? And these are the very simplistic choices. I'm going to switch to model control and say, well, the first choice what you can have is you can have a population 1, which happens to be called the model for monodispersed nanofeatures. So I said, well, let's assume I have a radius of 2 nanometers. That would be here. And I'm going to put a contrast there of 2. And then I am going to say I have a 5 volume percent of it. So a scattering of a 5 volume percent of 2 nanometer features, monodispersed features, would look like this. Let me make it somehow easier to see. If you do scale it up, you will see that you have these Bessel function oscillations, which is what you expect from monodispersed spheres. Now notice there is this flat background. Most of the data in the world will have a flat background. I just assigned an arbitrary number, which actually is common for my SAXS instrument. So the background actually limits how much of a signal you can resolve, because if the signal is weaker than your background, you may not see much. Now, most likely your system will not be monodispersed. So let's switch it off and go to population 2 and switch it on. These are now nanofeatures. This is 5 volume percent of 2 nanometer features, but they have now a size distribution of 10. Notice the contrast is still 100, so we can see something. And to show you, I can display a size distribution, and you can see it's a Gaussian size distribution around 20 angstroms radius. So there would be 2 nanometers in radius, and the full weighted half max is between 1 and 3. So that's again 2. So that would be 5 volume percent, but if this is really whatever the polycarbonate in water, then the contrast is 2, and this is what we see. That is all the signal you get. Now, if you now have a second population of features, which is now larger, so it would be what I call a submicron features. I gave them a size of half a micron, and this is what you see there. So there's a size distribution, 5 volume percent, 500 nanometers. This is a radius in angstroms, so that's 500 nanometers radius. And then I give it some full width at half max, so there are no Bessel function oscillations. This is so we can see it clearly. That's a contrast of 100. Let's give it 2. Okay. So now, if you have two completely independent populations, you will have the small angle scattering will sum together. So what we have at this moment here, we have a background. We have a scattering from the nanofeatures, and then we have a scattering from the submicron particles. If these two are not independent, if these two are in any way combined together, things get complicated and analysis get very interesting. So lots of times you're gonna see that you may have something called fractal aggregate, and I believe that's 5. And fractal aggregate also has a bend here and a bend here, and about the same positions, approximately. But notice they're connected by a power law slope, and the power law slope describes how they look like. And to show you what a fractal aggregate looks like is I generated one in IRENA. There is a tool in IRENA if you want to play with it. If you go in a 3D models, there's a mass fractal aggregate. and you can grow these guys in there. And this is a distribution of particles which formed in space a fractal aggregate. So it's like a snowflake. It's scattering, I hope this is the one. Nope, that's not the one. Then this is the one. Nope, sorry. This is the one, yes. So now the scattering of an object like this has a Guigneni at high Q, which reflects the size of these primary particles, these little spheres. Then it has a power law slope, which reflects how these particles are distributed in space, how much they fill the space. And then there has a Guigné area at around the large size, so there'll be external size of this feature. And this is what a fractal aggregate is. So that's another option. For fitting this in modeling package, there's a fractal aggregate form factor which you can use for it. And notice I just put here a note that unluckily the fractal aggregate does not really scale very correctly with the contrasts and volume. So that's not really a quantitative way of doing stuff. Anyway, so let's go back and say, let's assume that we have really independent features and not somehow connected into some kind of fractal or other large structure like a cylinder rod or anything else. So let's go back. Here we are. Number 2, primary particles. Number 3, the submicron particles. And notice the slope here in between them actually is Q2 minus 4. And the Q2 minus 4 means that the large features, these guys, have a smooth surface, and that kind of nicely separates these guys apart. Things get complicated if their surface is not smooth. If it's a rough surface, then you have a surface fractal, and things get a little bit more complicated. Now, in most cases, you will also find that there's other scattering. And the other scattering is, I'm going to add a 0 here. The other scattering is some kind of large structure. So if you think about, for example, a gel in water, and you have used a syringe or other method of depositing it in the capillary or an MR tube or whatever the container is, you may have created a bubble or multiple bubbles. If you have a solid piece of alloy or a metal or a wood or anything else, then you may have surface scratches on the sample. And those things will generally be a features which now have a contrast of air versus the material. And so if I assume this would be in this system, which is water and a polyacrylate, if polycarbonate, if I assume that I have added some bubbles, then the contrast of those is now air, assuming against water, and that contrast for those gives me about 89. So if I take now just 1/10 of a volume percent of these bubbles, so that is this scale, which is the volume fraction is 0.001, I give them a size of about 10 micron in radius. That's a size. And then I give them the contrast here. They will create a Guignée here, and then they'll create a power law slope. And they sum with the data. Of course, in most cases, you will not see this because this Q range here is in a 10 to minus 5 to 10 to minus 4 range, which practically no one can measure. So if you look on this in a normal case, your small angle scattering will look like this. And this will be the scattering which you can see. You can see there's a power law slope at low Q. It's still there. It needs to be accounted for in a model. You have some kind of feature here, and then you may have a feature here, and then you have a background. So this is a best guess model of what the user may or may not have. Now, if we go back to data control and say, okay, well, how do the data look like? Here are your data. And let me check this. Okay. And go back here and say, yeah, data controls and background 0. So the best guess is that we have a model which kind of resembles what we have here at this moment. We can go here and say this is 89. We can go here and say this is 2. We can go here and say this is 2. And you can see that we're not too far from what the data look like. At least we got the general shape quite well. Now, this is me looking at the data after many, many years of experience. But if you want to see yourself how the data really look like, and see how many of the features the small angle scattering tells you about, like, is this a feature or not? The best way to do that is actually to look on one of the linearization plots. Linearization plots are a Guinea plot, or a Porot plot or Kratky plot, and these are plots which tend to show the same data in different way, and the Porot plot is extremely useful. So I have actually added a tool here which anyone has available, and if you look on this tool here, even without the model, and I'm gonna now disable the model, so I'm gonna come here and say I don't have that, I don't have that, and I don't have that. So even without, and so what you see here is the background at this moment only. I'm going to zoom only in the range where the data really makes sense. So in this range, probably even below that, we can now start looking at it. So we have a background, and we can actually even do the fitting on the background here. We can come here and say, well, the background is probably slightly lower. So we can do a best guess of a background. Flat background in a Porot plot is actually giving you this slope here. Then you can see there is this deviation from the background. So that suggests that there is some feature here. And that one was the feature which we could do by using number 2. And again, you can do it in both of these. You can kind of come in and say, well, maybe this one needs to be going a little down, and then maybe the volume needs to go a little up, and just about like that. Now you're looking on a population number 2. So that gives you explanation for these guys. And now the good news is this is pretty much flat, and it's going to be flat if the slope here is Q2 minus 4, and you can figure it out by going in support tools and insert the Q2 minus 4 slope. Then you can go in and get tools and slide it here, and you're going to find out that you're pretty much looking on Q2 minus 4 here, which is what this, let me just remove this, which is what this thing is telling you. There's a slight deviation from that, but more or less good enough. So that would require a second population of features which have smooth surfaces, and that makes sense. While these are surely not spheres, turns out that the Guinea area for something like this is probably going to look about as spheres, and you can kind of, but if you think about these features, they have probably a smooth surface. So this would be a population here. And then you can play with it, and you can say, well, maybe what we need to do is go a little smaller. We probably need to go a little higher in intensity. You can actually go probably wider easily, and you can play with it, or you can just simply do a fit to it. Okay, and now we have an explanation for this. We have an explanation for this in one way. It's equivalent, it's just different presentation of data, which shows you the differences. And then remember that low Q power law slope, the whatever large stuff we have in there, Now, obviously, you cannot fit a guinea to it, but you need to fit somehow you somehow have to fit the slope there. And now you're gonna have to play a little bit more with fitting. There's a just small misfit here. Anyway, so this is multi-micron feature. That's the low Q one. If we do Control A here, you see that it goes to 10 to minus 4 and the data go to 10 to minus 4. If we come in here and say, well, why don't we enable also the wider range of data and then zoom out, you're gonna see that this part here of the curve, which you don't have any data for, you have to create some kind of structure which now fits this little tail of data. So you don't know much about it, and trust me, this is basically a wild guess which may be completely wrong. So it's just important. Oftentimes what we do is we just fit this with the power law slope and ignore any size related feature on that. Anyway, so the best way to figure out how many populations you need for fitting your data is actually hidden here in this little checkbox, which displays the intensity times q to the 4 versus q to the 4. Now, interestingly, if we go back to model and disable all of these beauties, how would the fractal aggregate look like? So if we go in and say use the fractal aggregate looks vastly different, because the fractal aggregate, there is a continuous connection between the guinea for the large feature and the guinea for the small feature size. And this power law slope, as I said, describes the way the mass is arranged in the 3D space. And you can see that in this Porot plot, it looks completely different. So if you see something like this, any assumption that you can model that as an independent, completely independent features is probably a bit of a challenge. Keep in mind that not every population will have a Q2 minus 4 slope as a Porot slope at the end. That means if you do this, this means that the surfaces are pretty much smooth. If you have a surface roughness, the slope's gonna be between -3 and -4, so it's gonna be shallower slope. So there are ways to do that, to get a different thing. Anyway, but if you are asking how many features you can really discern, and if independent populations are correct, and trust me, this is the most crude approximation of small angle scattering you can ever make. Don't ever quote this in a paper. And if you need study, a lot more details about how small angle scattering looks like, most of the small angle scattering is actually a lot more complicated than this. But this is the first step how to distinguish that. So if you look on here, this is clear and that is clear that there are differences, and the differences, something missing, can be solved by adding another population and hopefully fitting your data well enough. Okay, so that's it. Again, this is the crudest approximation of small angle scattering analysis I can imagine, and it was here only to basically show you how to try to guess from the small angle scattering data best number of populations or levels. You can do the same thing in unified fit, of levels of structure needed to explain your data, and do not overdo it. It's preferable to use less number of parameters and less populations unless you know better or the data are telling you that you need better data. Okay? Good luck.